all for this non-destructive testing and evaluation video lecture course. And this course code for this non-destructive testing and evaluation is ME8097 for the regulation 2017. So here we'll be studying in the 4th unit the ultrasonic testing. And before going in depth to the chapter, we'll just go through the syllabus. So unit 4, you will be studying about two non-destructive testing methods. That is, one is ultrasonic testing and the other one is acoustic emission testing. So in this ultrasonic testing, we'll be studying about the principles, the types of transducers, the transmission and pulse echo methods, the straight beam and angle beam instrumentation, data representation, and A scan, B scan, C scan, phased array ultrasound, time of light diffraction, acoustic emission techniques, its principles, acoustic emission parameters, and the industrial applications of ultrasonic testing. So coming to the introduction, the ultrasonic testing uses high frequency sound energy to conduct examination and make measurements. So this ultrasonic testing, which is applicable to most of the materials, like even metallic or non-metallic. And this ultrasonic examination can be conducted on a variety of materials, including castings, forgings, welds, and composites. So by these methods, even the surface and internal discontinuities such as laps, seams, voids, cracks, blowholes, inclusions, and lack of bond can be accurately evaluated from one side. So the sound waves normally have the frequency from 1 to 10 megahertz is used here. So this is the spectrum of sound. So the frequency range is from 0 to 20. You have this description as infrasound. Example for this is the earthquake. And the frequency range from 20 to 20,000 hertz is, you say it as an audible sound. And the example is speech and music. And the frequency range greater than 20,000, it's called ultrasound. Example, bat, quartz, crystal. So the basic principles of ultrasonic testing. Here, sound is transmitted into the material that is to be tested. So here you have a transducer, and this transducer has an transmitter and a receiver inside. So the high frequency sound waves will be transmitted by the transducer into the test specimen, and the reflected sound back to the probe is displayed on the flaw detector, that is on the CRT monitor. So that has been displayed here on the screen. In this figure, you can see that the distance of the sound traveled, that is displayed on the flaw detector, the screen, and that can be calibrated to give the accurate readings of the distance. So here the sound waves is travel from the top of the test specimen to the bottom of the test specimen, that is indicated by the red color line. And here the sound waves, when it reaches at the bottom of the test specimen, you have a signal called the backwall signal that has been displayed here. So this shows the backwall signal of the sound waves. And here in this diagram, you can see the defect inside the test specimen. And when the material shows the flaw detection, at the distance at the distance at which the defect is present, and that has been displayed here in the screen. So here you have a defect signal. This is a defect signal, and here you have the back wall echo signal. And here this slide, here the depth of the defect, that is the depth is around 60 mm from the top of the test specimen, that has been read out here in the screen. So that has been enlarged here, and here you can see that the distance 60 mm has been read out here. So likewise, you can find out the distance at which the defect is present from the top of the test specimen. And using this method, you can find the thickness or the depth of the can be measured for the test specimen. See here you have the different thickness of the test specimen, and that has been mentioned here as A, B, and C. So this thickness is measured, is read from the screen. So the thinner the material, the less distance the sound waves travels. And here you have, you can see the signal on the screen, that the thickness of the material, that is the bigger thickness is shown here as A and B, C respectively. And the basic principle of ultrasonic testing. So ultrasound transducer connected to a diagnostic machine is passed over the object being inspected, and the transducer is separated here from the test object or the test specimen by a couplant such as oil, water, as in immersing testing. However, when ultrasonic testing is conducted with an electromagnetic acoustic transducer, that is couplant is not required. So basically there are two methods of receiving the ultrasound waveform. One is the reflection and attenuation. And this diagram you can see, you have a transducer placed above the test specimen, and you have a crack marked inside, and the transducer transmits the sound waves into the test specimen, and the sound waves, when it reaches the crack, you can see that has been reflected from the crack, and the sound waves is received by the receiver inside the transducer. So all this has been displayed on the CRT monitor. You have a initial pulse, that is from starting point from the top of the test specimen, and the second, here you have the crack echo. So that is the defect in which you have this signal, and the back surface echo is the bottom part of the test specimen where the sound waves reaches. So normally the sound, you have the wavelength, frequency, and velocity, which is very important for the sound waves. So the wavelength is normally the distance required to complete a cycle. It's measured in meter or mm. And the frequency, that is the number of cycles per unit time, measured in hertz. And velocity is how quick the sound travels, distance per unit time, that is measured in meter, second, etc. So the basic principle of sound here is the sound usually is produced by vibrating a body, and that travels in the form of wave. So sound waves will travel through the material by vibrating the particles that make up the material. And here you can see the diagram, and see some force is applied on the material by a hammer. So you have the pitch of the sound is determined by the frequency of the wave. So here ultrasound is a sound with a pitch too high, that is to be detected by the human ear. So this shows the sound wave propagation, and you can see the small particles inside. So these particles vibrate, and thus the sound waves will transmit from one end to the other end. So properties of sound waves. Sound cannot travel in vacuum. Sound energy to be transferred from one particle to another. So this is the sound waves. So sound waves transmitted through materials which behaves in an elastic manner. You have three types of waves: longitudinal waves, transverse or shear waves, surface or Rayleigh's waves. So with this we come to an end to this session, and thank you. Have a great day.